So let's talk about super tagging with attentive graph convolutional neural networks. I mean, the article in 2021 by Tian, which is a really interesting article. But there are other articles like this one from Stephen Clark, very similar ideas. Very similar ideas you can find here, but all of them are talking about CCG semantic parsing. So in this paper, they propose attentive graph convolutional networks to enhance neural CCG supertagging through a novel solution of leveraging contextual information. This is important because in language modeling, for example, when you talk about n-grams, I will create a new playlist about probabilistic language modeling because it's really important. And nowadays we try to augment, to take advantage of contextual information in almost all of the models that we have. Because it's something that can be trained in an unsupervised way. That's why it's very important. So they build a graph from chunks, those n-grams that I told you. So extract it from a lexicon and apply attention over the graph. So it's not just like convolutional graph convolutions, but also it's attentive because it says what kind of weights. And so they propose attentive graph convolutional, let's say GCN, for CCG supertagging, where its input graph is based on chunks. Before this article, people used to take advantage of dependency parsing for that, but now we understood that if we use dependency parsing, then all of the problems of dependency parsing will flourish, will come to our new problem of super tagging. So all problem of dependency parsing. But the interesting idea of this paper is that instead of dependency parsing to create our matrix, our adjacency matrix, we use just the n-grams, because if we know the n-grams, then we know which words are together, and then we create the dependency matrix that this algorithm needs, finding super tagging. So this paper, so instead of here, it needs an adjacency matrix, and people used to use those dependency parsing for this, but now they understood that so that is a problem, and all of the problem, and we always need we should rely on a good dependency parsing. So instead of that, now we are using these n-grams. For example, 3 grams by some books, and so we can create adjacency matrix very fast, very accurate. At least more accurate than those dependency parsing, and after that, we give it to our model. Here we are using, you see, probability of this. So in this graph convolutional neural networks, it should be indifferent to different nodes. But in attentive approach, it is not conservative. It's for example, says this weight is more important than this weight. So it has some priority over nodes. And after that, layer by layer, we build on that. We can go to higher n-grams. We can create new layers. And finally, we say that we have a softmax and say that what is the probability for MP at this time? What is the probability of this at this time? And so on. And so, just like usual, the Elf layer of graph convolution neural network is built on a linear combination of the previous layer, but we also we always multiply it with their adjacency matrix, because A could be either 1 or 0. If it is 1, it means it's adjacent. If it is 0, it means ignore it. So ignore it, so it automatically ignores that because that's not adjacent. So in this linear combination, we only care about those adjacents. So I is adjacent to J from 1 to N. So I has some adjacent nodes, this graph. So 1, 2, 2, N. So I has N adjacent nodes. So that's why the linear combination of these hidden representation is here. So even it isn't now much more powerful than attentive bi-LSTM in previous approaches that people used. And also here I will show you something more. So a sentence, as I said, we compute PMI of two words and use a threshold to determine whether a delimiter should be inserted between them. Okay, so this is the probability. But here we have two types of edges. It is cross-chunk or in-chunk, because sometimes we have trained our engram differently. That's why it says all students should come together. Are required should students are. So you see there is a gap here because we can modify it and we add more details. That's why we have two types of edges: cross chunk and in chunk. In chunk is usual. It is trained like the engram suggests that, but cross chunk, it says although our engrams is the same, but sometimes we add some new words. That's why it makes our engrams look different. Look that it is not working, but we have two kinds of edges. This is interesting. And as I said, all students are required to finish. So in these chunks, all students finish in 2 hours are non-overlapping engrams. And are required to is a text that covers the overlapping engrams. Are required and required to. So in most cases, adjacent words within the same chunk tend to have a strong word-word relation in terms of co-occurrence, and thus we can build the graph and its adjacency matrix accordingly. So as I said, we have two types of edges. And so when we say a GCN, it means that attention plus graph convolution or neural networks. So I told you now, because it is attentive, our weight, we should not work with standard graph convolution neural networks because it is now priority over them, over these edges. For example, from I to J, depending on I and J, so there is a matrix that W that should be learned. So we learn this. That's why we understand which PI, what is PIJ, what is this probability. So from L-1 layer, you go to L layer. This is point. And so what is this PIJ? That is the probability that is here written PIJ, PIN -1, but all of them are for previous layer. And then, so putting this here, we understand that now it is attentive graph convolution neural networks because, for example, PIJ is different from PI and J plus 1 and so on. So after we have done this, so we are until this layer. So we give it to ReLU linearity. So we are here. H is equal to here. So we are here. H, we have calculated the H, the hidden representations. And after that, we give it to another trainable matrix for alignment. Because now we want to give it to softmax. So softmax of, so let's say this is just the softmax of OI. So, and we take the maximum of that. What is the probability of each one? For example, the maximum could be this. The other maximum could be this at another token. So we take the maximum, and can you do better? I mean, all of them are more than 91%, so it's quite good. Maybe this one, but for this paper that is using attention and graph convolutional neural networks, it's getting more than 90%, so it's good. 90%. But you may say, so is this CCG over? No. In this paper, we are just talking about super tagging. We are not talking about logical forms. You know, if you are talking about lambda calculus formalism, of course, don't forget that CCG, don't get me wrong, CCG can be combined with AMR, abstract meaning representation, lambda calculus, and anything else. So here, because we are talking about CCG. What is CCG? It has a super tag and also this logical form. Super tag. You know, most papers just work on super tags, but they I don't know why they ignore the logical form. But they should be combined. They should be considered together jointly. That is the challenge. That's why you will never get 90% these days. That's why it becomes challenged. But if it is supervised, yes, you see all of them are great. Everything is more than 90%. Everything is easier. So it is good to write an article that has a very high accuracy, but we consider these formalism as well. At least pick just one of these formalism. All of them are just formalism. Just pick one of them, one of these semantic formalism, and then combine it with super tags. Even learn it jointly or condition on that. So there are two approaches.